welcome Professor Miguel Dumett, who was my main collaborator in Mimetic methods and application. I'm going to give you a tour de force from the beginning to where we are right now and where we're heading in the future.
Thank you, President. Thank you for the invitation. Okay, so instead of preparing or talking about directly about Mimetic methods, I will try to do some sort of introduction, some sort of motivation. And so, oops.
Well, I have to be closer than you have.
Okay. Oh, yes. Okay. Sorry. So, suppose we have one of these equations, simple equations. Laplace to the potential equation, we have the heat equation, and we have the wave equation. And the equation is given with a certain boundary condition. Okay. So, I would like to replace all the differential operators by metric representations. It's something just to remove the PDE characteristic of the equation and convert it into an algebra or a system of ODEs, but in a very convenient way, very simple way. And so, suppose that this is a 3D problem, and I will approximate the Laplacian go by certain matrix. And the x, y, z indicate that the Laplacian, it is a Laplacian, and in the end, I will convert this system into a linear system. F is the discretization of F in a certain grid, and U is the numerical solution, and A is a representative of the Laplacian. And so, if I have this partial differential equation, I get first a representation of the Laplacian, then I add somehow the boundary condition, and I construct the system and solve the system, and we have the solution. Okay. So then another equation is doing something similar. We approximate the Laplacian, so remove the special derivatives with this technique. So first, I have some sort of Laplacian representation. Then I add a discrete version of the boundary condition to the Laplacian. And then I have a system of ordinary differential equations. And I could use any solver that I want, or I could discretize on time. So again, this equation, this monster equation, which is a partial differential equation, with this technique, we are removing all the special operators just by substituting those by matrices. And that becomes a system of ordinary differential equations in the worst case scenario. And the same here. So again, we have an approximation of the Laplacian. We incorporate or complement the Laplacian with the boundary conditions. And we now have a system of ordinary differential equations. You can discretize in time or apply any, for instance, MATLAB solver for doing that. Okay, so for simplicity, in that context, so I am still talking in abstract, and I will consider scalar and vector fields. Why I am talking simply, or I say simplicity, because we could, as you will see later, we could be in the context of vector calculus, tensor calculus, or exterior calculus. And just for simplicity, let's assume scalar and vector fields. And we know what is a scalar field. A scalar field is a function that has several arguments, and it will return a real value. And a vector field has several arguments and return a vector. Okay. And we know that If I have a gradient, I apply the gradient to a scalar field. And if I have a divergence operator, it applies to a vector field. In addition, the gradient of a scalar field is a vector field, and the divergence of a vector field is a scalar field. So they have this symbiosis or symbiotic relationship. And so that invites me to, since these two scalars and vector field in some sense are two animals or different species, I would like to have one grid for each of them. So I will work with two grids. And for that reason, we work with staggered grids. As I said, I would like to remove all the spatial differentiation, but just by matrices. And this matrices acts on vectors. If I have a three-dimensional domain or a two-dimensional domain, I will have to convert that into a vector to apply this operator and obtain the result, which is a discretization of the gradient or divergence. Okay, so again, in abstract, assume we have, suppose we have a Cartesian domain, and in that Cartesian domain, we consider Xn, which is the set of cell nodes in 1D, or edges in 2D, or faces in 3D. And Xc is a set of cells and vertices. So the discrete scalar fields live on Xc at the centers. And the discrete vector fields will live on the nodes, or on the edges, or on the faces. And the approximation for the divergence, the matrix representation, will be an operator that actually goes from nodes to centers. The gradient will go from centers to nodes. And the Laplacian, since it's a combination of the divergence of a gradient, will go from, should be, what's going on here? Oh, yes, I apply first the gradient, go to Xn, then the divergence, and go to Xc. So Xc. Okay, so these are, again, some things that I have to get in order to obtain a consistency of what I mentioned before. So doing this abstract representation, removing all the differential or differentiability with respect to space. Okay, so
may I make a comment? You moved that back one second. Okay. You said operator represented by matrices, they act on vectors. Here there is something, we're talking in the computer, or we're talking in a vector space?
No, I am talking now in the discrete.
Yeah, but the thing is that when you take a 3D and then you make it to, that's called an array, because that thing doesn't have any direction or anything.
Yes, but the operation is called vectorization.
Ah,
For that reason, I call it that. Okay, and so we have a list of operators that usually show up in vector calculus, divergence, and the discrete version we will call D. So the gradient, the curl, the Laplacian, and then we will have also some interpolation, because you'll see that there are certain quantities living in a grid and other quantities living in another grid. And there should be a way to pass from one grid to another. So I need an interpolation from, let's say, from centers to nodes, and another one from nodes to centers. And if I want to also, since we are in a context of vector calculus, approximate integrals, I will need some high order quadrature. And these are matrix representations of them. And again, D, for instance, the gradient, as we said, go from Xc to Xn. These are two different sets.
Is that, does the interpolation have to do with that mapping from one space to the other? Or I'm using space loosely, but is that what the interpolation has to do with?
Yes, it will go from one grid to another, because there are two. One for the nodes and another one for the centers. I will show you a picture. I am just talking for now, properties that I would like to have for how to handle this. And so the matrices are non-square because they go from one to another grid. The number of elements, you have 10 cells, you have 11 nodes. So the number of elements is different. Okay, so let's actually now, the previous equations were very simple. Now let's try to face another example that is more elaborated. So in this particular case, you have a non-linearity. There is u times the derivative of u. And so let's see what happens in that case. So let's actually try to introduce this algebra that we have. So the idea is to substitute all the continuous quantities that show up there and the differential operators by matrices. So if I will do that, I am just replacing the differential operators, and I am having u the continuous variable, and u and v also continuous, and u and v uppercases are the discrete version of these quantities. And somehow I am vectorizing this. So they will be, my discretization will be vectors. And so what I will do is just substitute that in several steps. The first one is ut, so the lowercase u is substituted by the uppercase u, which is the discrete version of u. But this is the derivative in time. Then u, and we have here the gradient of u with respect to x. If we assume that u is a quantity that lives on the centers, this derivative is a gradient. Okay, and we have the gradient of x of u. So this circle indicates certain kinds, some sort of multiplication between the two. And the same happens here. V is the discrete v. There is this sort of multiplication, and this is the gradient of u with respect to y, which is u is a vector and y is a matrix representation of the gradient in such that the product with this u will give me the gradient of y with high order of factorization. And here we have, this is the Laplacian operator operating on u. So the discrete version will be L times u. So I have matrix times vector is vector. This is a vector. This is another vector. There is an operation between vectors here that we have to fix. And here is a vector again, another vector, and a vector. So we have vectors. I don't know if they are of the same size. They are not. Because if u has n components, this will give me something different. But v is in n components. So these two vectors have different components, and I have to do something. The thing that I will do is, since this is off the centers, so u is in the centers, and gy of u is at the nodes, so the product is at the nodes, then I have to move that to the centers, and for that I will use an interpolation. And so, introducing interpolations, so we have an interpolation here, which goes, it's interpolation that goes from nodes to centers. And this is an interpolation that goes the same, but this is in the x direction, this is in the y direction. Okay, now I have a vector here and a vector here. They have the same number of elements. And now this product will be an element-wise product. Okay, so this is, but I want to convert this element-wise product into a matrix times a vector. And for that, I introduce,
I'm sorry, just to be clear, when you're saying vector, you really are meaning array.
Array, yes, sorry.
And u and v are scalars here.
Yes.
Define on
On a center, yes. One of the grids, yes. So again, I will substitute this operation by diagonal of u. I will write this component-wise multiplication can be written in this way. This is a matrix, array. Okay. And the same in the other side. So we are step by step converting this. And now you see you have vector and I have, array, and this is matrix, matrix, matrix array, matrix, matrix, matrix array, and constant matrix array, all of them of the same size. Okay, so now we are ready. So we have removed at this point all the spatial derivatives, and we have only the time derivatives to apply. And still we have to deal with these u's. There is a u here and there is a u here. And also in this other component, I am working with the first equation only. You can work at the same, similarly with the second. And in the second, we have a u, a vv. So if we use, for instance, forward Euler, it will be un plus 1 minus un divided by dt. The dt can go and multiply everything, and it will be show up here, multiplying all these terms. And it's supposed also to multiply this other side, which is that term. And there is an un that will go to the other side, and the un plus 1 stays here. And the way to avoid multiplying these u's, I will assign this to n plus 1 and this one to u as information. So this quantity is already known at a particular time step. And what we want to find is un plus 1. So writing that way, you have this, you have that. For the other equation is this, and I can iterate.
So U and V are 2D arrays. I don't understand
U and V are
arrays, right? They're
Array.
defined on X and Y.
converted in as a vector.
A
Vectorized.
subvector, but so what does diagonal U mean? Why would that be chosen instead of, say, the eigenvalues of U, of that array?
No, because over here, let's go. So this is U1, U2, U3, let's say.
Right.
And this one has 3 components too. This product is first component times first component. The second component of this product is second component of this times second component of that.
Right.
And third component times third component. So if I write this as a diagonal, having U1, U2, U3 along the diagonal, I will know that.
So you're just trying to write this in the form of a matrix.
Yes, to be in the territory of just matrices and vectors. Okay, so now I have the scheme, and this is what I will implement. That's my code. Okay, so far I haven't told you anything about what is G, but you understand the idea. So I will find representation for these matrices somehow. Okay, and so now let's do it a little bit, showing how these are constructed. So suppose I have the centers and the nodes. This is what I was calling XC. I have the centers and the nodes. And here I have the, let's say the blue ones plus the extremes. Sorry, what is this? So, no, and here I have the phases, 0, 0.2, 0.4. And so the gradient takes information from the centers and move it to the nodes. And the divergence takes information from the nodes and move it to the centers. Okay? So this is just a graphical representation of what is there. And how could I construct this? So suppose I want a high order gradient going from centers to nodes. I will assume that the distance between centers or nodes is h, and there is a point h over 2 over here. So the idea, having a second order, for instance, approximation of the gradient at this point, I will use the two here of this to construct this. It's very easy to obtain the second order. The trick is how could I obtain second order on the boundary? And so the idea is to use this center, and the information over here. So the gradient at 0 will be a linear combination of the value at 0 the value at h over 2, the center, and the value at the middle of this cell. And what I do is I just expand in Taylor around 0, match coefficients, and I get 3 relations for 3 unknowns, and I get these values. Okay. And I could do it for 4, 6, 8, or any order. Okay. And so that way, when I construct the second order G, it's 1 over divided over H. If you actually observe this, I will have H. And also, if I try to calculate the gradient in this point, there is a formula divided over H. And so the 1 over H goes out, and this is the formula that I get. This is the usual central differentiation for the points that are in the middle, and the points in the boundary require a special treatment. In fourth order, I will have the coefficients. We have those, and there is a report that we published, and it has all the gradients for really 6 and 8, and divergence and interpolations, and so other stuff. Okay, so basic properties of this. First of all, if I want the gradient of a scalar vector, of a constant scalar field is 0. And if I suppose I have a scalar field at least 1 everywhere, if I apply the gradient, that should be 0 vector. So, and that happens, that G times 1 is 0. So this is replicating the property of the continuous. How do I know I have this? Well, it's simple. When I match these terms, I will see that A plus B plus C is 0. And A plus B plus C are the coefficients that are here. And so I am enforcing that in the derivation already. Okay. Similarly, the divergence of a constant vector field is 0. Has the same property. That translates into 0 row sum. Another thing that is important now we are just talking about, start to talk about mimetics. Okay. So why do we want mimetics? Mimetics are numerical methods that replicate characteristics of the solution. For instance, symmetries, conservation laws, and other things that I would like to. Historically, they were targeting some of these characteristics, but nowadays, mimetic methods are divided in 2 categories. One of them sees all the properties that can be obtained from enforcing some vector calculus integral, like the divergence theorems, Stokes theorems, Green's theorems, or any of the extensions of these theorems. And there is another collection, more recent methods, that instead of enforcing the integrations, the theorems of integral theorems of vector calculus, what they do is they enforce the calculi or the calculus of the operators, of tensor operators, of exterior derivatives, and so exterior calculus. So they enforce the properties, and from there they get the integrals. Yes.
So where do the degrees of freedom you need in your parameters come from to enforce these conditions? Does that make sense?
Yes, you'll see it here.
Okay.
Here. So when I
Make a comment?
yes.
Not related to that, but believe it or not, finite difference is the most widely used still in method to approximate derivative. But you can get, using finite difference, you can get a function. Okay, you compute the derivative using finite difference, and you get 0, but the function is not constant.
Yes, that's right.
And that means that the error will propagate the solution of whatever problem we do.
Yeah. And so let me just answer your question. So if I want to, this is the integration by part formula. This is in 1D. If I think about the extended Gauss divergence theorem in 3D, and I actually reduce it to 1D, I change the domain by an interval, and it becomes integration by parts. And so if I want to enforce this, second order is fine, I could do it. But when I want high order, I will run in trouble. I don't have enough degrees of freedom. And so what I will do, actually the original paper written by Castillo and Grant, do is they introduce weighted inner product. And the degrees of freedom shows up here. So I am gaining degrees of freedom right there. And so I convert this integral as an inner product. Like if this is the gradient of f, this is the discrete version of that. And this indicates an inner product weighted by p, which is diagonal matrix. And h comes from the base of the rectangle that approximates the curve. And then we have the divergence of b, f. And I get this is the boundary that has in the interval only two boundaries, is the product of this in one direction, in one extreme, and the other one. And so from here, just by giving, assuming that f is constant, for instance, I could get a version of the fundamental theorem of calculus that actually gives me some properties that I'm supposed to have to make this valid. And if I do it also for a constant vector field, I will get this other property. That means this is the way we define Q and P. This is a linear system. This is a constant times a diagonal matrix. This is the diagonal of Q as a vector. And we have a system to solve to find Q. And so that is in 1D. Oh, yes. So in 2D, the two grids, I have superimposed these two grids here. One of them is in blue, and the other one has red horizontal lines or red vertical lines. So in blue is where the discrete scalar field lives, which are the centers and the boundaries. And in red, we have the vector fields living. This is the first component of the vector field in 2D. That's the second component of the vector field in 2D. Okay? And so the operator B, which is the divergence, runs from nodes to centers, which is all the numbers that are with an index V or W that go to a point that has an index F. And the gradient goes from the centers to the nodes. Okay? So it is more elaborated here. Okay. Now I will talk about what happened. We have seen what happened in 1D. Now let's talk about what happened in 2D and 3D. So the way to do it is via the Kronecker product. So just to refresh this concept, you have A as a matrix, B as a matrix. The Kronecker product is this entry times that vector, the second entry times that vector, and so on. Okay, and using this notation, we can show that whenever you have a discretization, you want the divergence in 2 dimensions, you will use the divergence in 1 dimension times a Kronecker product with certain matrix, which is essentially a matrix that is the identity plus 1 row of zeros on the top and 1 extra row of zeros on the bottom, which is this. And in 3D, you can write the divergence that way. So it's a very elegant way to write these operators. Okay, using these properties that we have found and the construction of these 2D and 3D operators, we were able to prove that, so several identities from the vector calculus. I wouldn't say all of them because we didn't try all of them, but whatever we tried, we were able to prove. And so at least 12, 15 identities. And so if I have a scalar field and another scalar field, then if I try to replicate this property, I am able to do this. I will need for sure interpolators because these two quantities live at the center and the result will live on the nodes. This lives at the center, this is already the nodes, and this is at the center, so I have to pass from to decide where I will do the computation, and the same happened to here. Okay, so at this point, Jose, you correct me this because I am not sure. It's my impression that there is no other method that was able to prove this property.
I know for sure that the spectral method, which is widely used, doesn't satisfy the protocol.
So, and also the divergence of product and the Laplacian of product. Okay, those are, again, for any F and G, or F and V, or F, G, and yes, these are proved. Okay, so we have this. In addition, we were able, using exactly those properties and nothing else, we were able to show conservation of mass for any system of conservation laws. And we were also able to show energy preservation for some conservation laws and for the advection equation. And so this is an example of a two-dimension. You see it's two-dimension because F has two components. And there are four conservation laws. This is density times horizontal velocity, density times vertical velocity, and energy. Okay, so this is a conservation law. These are called the Euler equations, and this is conservation of mass, conservation of momentum, conservation of energy. And so,
I'm just having a hard time going from this mathematical formalism to these physical quantities. I mean, on what basis do you call something mass? Or do you say it satisfies the conservation of mass? Does it have to do with?
just what I mean is the integral of the variables is conserved. Okay, and in this particular case, the mean is mass, but it could be any other thing, but I call it mass.
Okay.
But for energy, I call the quantity squared. Okay, and so this system of equations needs to be closed, and we close with a relation between P and the density. The exact solution is given to this. This is very hard to find an exact solution for a system of conservation law, but we found it in a book, in a numerical methods book for partial differential equations. And so when we apply our techniques after running 100 units of time, we see this kind of solution. You'll see this, the progression, it is conserved. We use a Corvino-Castillo for order mimetic method for the space and leapfrog for time. And you'll see here that these quantities are conserved. So the top one refers to the energy, this one refers to the density, and also the momentum in U, and this is the momentum, the vertical momentum. And then, in addition to that, using exactly, again, this technique, these formulas, and whatever is known for the theory of convergence, so using Rich-Mayer theorem, and using a local differential error, stability, and consistency, we're able to prove that for instance, a 3D advection system using a special method for integrating in time. This is not a method that has special properties. I have chosen that method because it is a method that computes the next step in time by producing several intermediate stages. So it is more complicated to do. And so when you have the divergence in 3D, the advection in 3D, you have an equation like this. And when you actually discretize, so you apply these techniques and you get to, so if you discretize this in space, just the part in space, you will have that this is KD times U, where K is this matrix. Or if you use, instead of using the divergence, you want to use the gradient, you will have this sort of matrix with the gradient over here, and there is an interpolation here. There is another interpolation there. Okay, any of them, it's essentially a matrix K times U. And so this is the method that we use for the integration, the discretization in time. And this method actually will compute will need for these different quantities. And what it does, it will iterate from this to the next quantity following these formulas. And so this doesn't have to be anything with Mimetic, it's just a method. And then when you actually collect all this information, you will get a Mimetic setup, and then if you define local integration error, you will be able to find consistency, stability, and then convergence. So there is a proof, we have published that, and you see clearly here the convergence for the mimetic scheme for that vector. This is something that is moving, and you have the exact solution and the approximate the two steps in the evolution of the solution. And well,
I make a comment just to say.
yes,
Just for the record, we don't recommend that times discretization scheme to anybody. It turned out that there was I don't know, it's misinformation. This is very popular, this word today. So when I found this paper, it was presented as a fourth order leapfrog. And it turned out there is only second. After all the work, he only delivered second.
yeah, you found it
But it was for the purpose of this, it worked, you know, everything, but it's a lot of work, and well, we can use leapfrog second order and we get the same.
yeah. So, but it was a good exercise in terms of having the machinery to prove convergence and stability and.
All right, so there's nothing special about that particular temporal integration. It
Well,
just-
that conserve energy, because we have, in this case, energy conservation in space
In space.
and time. That was the only thing.
And then, so we do all this, the numerical part using MOL. MOL is a library for mimetics that was developed here at the university by Johnny Corvino. And well, here are some of the instructions to follow. It actually is a very nice library in the sense that it has all the code available. You can see the implementation in MATLAB or in C++. And in addition to that, there are many examples you can actually follow. For instance, this is one example, a Poisson equation in 3 dimensions. You see essentially, you're cleaning the environment from the beginning, telling the library where is the code. Here you set the level of accuracy, the number of cells in each direction. You call the Laplacian complement with the Robin boundary conditions, which in this particular case are Dirichlet boundary condition. Then construct the right-hand side, solve the system, you have the numerical solution. And sorry, the right-hand side was in 3 dimensions. It's converted into a vector using this MATLAB function, and find the numerical solution, go back to the original form, and just choose the second phase of the 3D to plot, and this is plot. That's as simple as it is in Go.
Suppose that Pat wants to implement this. He doesn't want to use this library, and he wants to program all these operators. How many lines of code?
I don't know.
A lot.
I don't know. So it's a simplicity.
Well,
It's a simplicity.
Just
Well, I'd be grateful.
Yeah. So my point is this: it is simple to understand.
Yeah.
You have partial differential equations. Forget all the special operators translate into matrices. And so now I am in a territory that I am well aware of, right?
Well,
In matrices.
it's a different way of thinking, you see, and that's something that it takes some used to it.
And the
When
library,
you get used to that, you see that it's actually really easy, and you can do any PDE.
and the library is well implemented. It's actually it's very simple to understand.
Also very highly computationally efficient, because even though, forget about the MATLAB, the C++ version, we do have all these operators already there, but we know the coefficients, so we use them. So we don't actually construct the operators every time we're gonna solve the problem. And that makes a big difference.
It's a functionality already implemented. Yeah. Just a call like that. And then going back to what is called fully mimetic. So this is scary at the first sight, but it's not, in the sense that this is trying to summarize all different calculi that exist. So on top, you see, this is some sort of a building. There is a front part of the building, and there is a back part, and there are six or five.
10 floors.
6 floors, yes. Well, let's consider this one floor. And so the top floor is a theory for continuous vector calculus. The second floor is the theory, the continuous theory for tensor calculus. The third floor is the continuous theory for exterior calculus in differential geometry. This is the discretization of the exterior calculus. This is the discretization, this floor is the discretization of the tensor calculus, and this is the discretization of the vector calculus. Whenever you have, let's actually focus on the vector calculus because it's probably the one that we know best. So we have here a scalar field. When you apply the gradient, you get a vector field, and you can apply the curve, and you get another vector field, and finally you apply the divergence, and you get back to the scalar field. And so when you try the Laplacians are operators that go from here and do perform one of these loops. And so you see there are 3 Laplacians here. We are aware only of one. There is another one that is called the vector Laplacian, which is exactly this. And there is another one that is called the graph deep Laplacian.
We're aware of it. We haven't built it, which is different.
Yes, but exactly. Yeah. Well, but I mean, it's just for people, it's not aware of that in general. Okay,
So
so
those operations used in solid physical systems.
So in addition to that, we have, for instance, as I said, you use what is it? Okay, over here. This is the exterior calculus floor, and in exterior calculus, the divergence, the rotational, or the curve, and the gradient are just the same derivative applied into different elements. And so the notation is d, but you understand that they are going from different spaces. And you know by context, where are they? On the other hand, there is the front face, which is using actually the primal grid, and is the back face for the dual grid and the dual operator. So again, now what I meant for calculating, when I was telling you that this fully mimetic actually tries to replicate this calculus. For instance, when I have anything here, if I apply a gradient and then a curve, I will get 0. So it's a double exact sequence. Okay, so again, this is a new understanding of fully mimetic method. The method that was developed here at the university is not a fully mimetic method, but we are trying to go and embed our method in this framework. And it's different because all other fully mimetic methods, they increase accuracy by adding degrees of freedom in the polynomial approximation in each of the functions in each element. The way we get higher order is by looking at the neighbors. So, and there are several things that several properties that the method developed at the university has that no other method. In particular, that we can get uniform degree of accuracy, including the boundary. And there is no other method that can do that, even mimetic or not. Okay? And so this is all what I wanted to tell. You know, this is trying to beginning with what would be the ideal way of passing from PDEs immediately to a matrix equation. Leveraging on that idea to introduce the mimetic, and this is essentially what we have developed and we are developing. Thank you.
The floor is open for questions.
Yes.
Is the library able to work with PDEs in spherical, polar?
Oh, that's a good question. Actually, yes, there is well, yes and no. It depends. Normally, when you have a curvilinear domain that is the result of a mapping, a differential mapping from a Cartesian domain, yes. Any curvilinear domain that you think as you know, as just one application, yes. But when you have several of them, this is a problem that we are studying right now. So we want to solve that when you construct a surface by different mappings, just a collection of overlapping mappings. And something else that I mentioned, that I didn't mention, is that even if you use Cartesian grid, but with non-uniform spacing, it's already implemented in the library. Okay. Yes.
So can you say anything about the operations that go from one floor to the next? Like, it goes from a vector to a tensor? I mean, what sort of operation does that include?
Well, there is I don't want to go into that data, but it's a bijection. It's essentially bijections in between them. You know, even though they are different animals, the number of dimensions each of the components is the same. It's a rename. So you could probably get rid of this level and just focus on the exterior calculus and work on that. And whatever you get here immediately will replicate it.
Yeah, but also a lot of things has a different name. For example, a matrix is also a tensor.
Metric.
And there is another, now you mentioned this, there is another thing. You see, there are some certain integrals here. And it's the projection of the continuous space to the discrete space. In all the fully mimetic methods, what they do is they integrate over the domain and give a number. So the discrete version is the integral of a domain. In our case, we don't do that. And it is this integral or it is an average integral. So it's an integral divided by the volume of the element. So any of these two, depending on if, for instance, you have Steinberg discrete tensor calculus is using something like this. Or what was the name of this guy from Holland?
Gerishman.
Yes,
Mark Gerishman.
Gerishman. So Gerishman does it for exterior calculus. He just integrates, and so depending on the authors and the methods, they will do something like that, just focusing, converting the integral of a domain into a point by projecting. They call it projecting. And when you try to get back, the way you will probably use some polynomials to interpolate the data to get the continuous. And depending on the set of polynomials you use, you're talking about finite elements, you're talking about Poisson volumes. And also I forgot to mention these diagonal arrows, which are the Hodge star operators that relate one particular dual space with one of the primary spaces. But again, you know, there is a lot of mathematics here. We are not yet there. We are trying to see how to embed our method in this, or modify it or adapt it. Let's see how it goes. But we're working on that.
What's preventing you, like, exactly from doing it in any type of mesh or coordinates? Like, what property is preventing you from doing that?
Oh, because when you have an structure, for instance, something trivial. If you have a a set of triangles in a mesh like that. Then how do they map this into that? So I don't have unless this is just a deformation of that, or unless I convert the triangles into some sort of deformed squares, and I am able to somehow map this into that.
It's like a wing of an airplane wouldn't work.
Well, you can, the wing of an airplane is an easy one.
Yes,
Map into a
but,
radar.
but imagine the brain.
Hmm.
The brain is much more complicated. So it depends on the geometry that you have. But again, so we are working towards that. There are several ways of doing it. In particular, we are, as I said, we have several lines of research. One of them, for instance, is trying to solve interface problems. When you have, for instance, in the brain, different tissues, and you are investigating electrical activity of the brain, and there is conductivity that changes from medium to medium, and well, when you pass from one media to another media, there are certain jam conditions, the continuities or the normal derivatives, and so on. You know, there are certain things, and we are still also looking for applications in electromagnetism, in continuum mechanics, and so on.
Any other question? Okay, so we.